Imagine a world buried for millions of years under kilometers of solid ice. A lost landscape of mountains taller than the Alps, vast canyons, and freshwater lakes the size of countries, all sealed off from the sun and our world. This isn't science fiction. This is Antarctica. We see it as a flat, white expanse, but beneath that frozen veil lies an intricate, ancient, and surprisingly dynamic world. Today, we're journeying into this hidden realm, exploring the science of subglacial hydrology, the incredible technologies that let us see through the ice, and the tantalizing quest for life in one of the most extreme environments on Earth. Before Antarctica descended into its deep freeze, it was a very different place. As part of the supercontinent Gondwana, it had a temperate climate, with flowing rivers and lush forests. But around 34 million years ago, as the continent drifted south, it became climatically isolated. Ocean currents that once brought warm water were cut off, and the cold took hold. The very mountains that once guided rivers became the birthplaces for glaciers. These glaciers grew, merged, and coalesced into the colossal east and west Antarctic ice sheets we know today, burying the entire continent under an ice blanket that is, in some places, over 4 kilometers thick. You would think that the immense pressure and slow, grinding movement of all that ice would have scraped the land beneath into a flat, featureless plain. But in a fascinating geophysical twist, some parts of the East Antarctic ice sheet became so cold that the ice at its base barely moves. This extreme cold has acted like a preservative, flash freezing an ancient landscape in stunning detail, protecting it from erosion for millions of years. For most of history, what lay beneath that ice was a complete mystery. The first clues didn't come from looking, but from thinking. Russian geographer Andrei Kapitsa theorized that heat rising from the Earth's core, combined with the immense pressure of the overlying ice which lowers the melting point of water, could create pockets of liquid water at the base of the ice sheet. It was a radical idea, but the first physical evidence for a world beneath the ice came by accident. In the 1950s, pilots flying over Antarctica found their radar altimeters were giving bizarre, useless readings. These devices were supposed to measure the distance to the ground, but something was interfering. It turned out the radio waves weren't just bouncing off the top of the ice, they were penetrating it. This anomaly sparked an investigation, and in 1957, researchers proved that radar could indeed measure the thickness of the ice. This was the birth of one of the most important tools in modern glaciology, radio echo sounding, or RES. Think of it like a powerful fish finder for ice. A device transmits radio waves downwards. Some waves bounce back from layers within the ice, but the most important echo comes from the boundary between the ice and whatever is underneath it: rock, sediment, or water. By measuring the time it takes for that echo to return, scientists can map the thickness of the ice and create a picture of the landscape below. In the late 1960s, scientists using this new technology saw something strange in their data: unusually strong, sharp, and perfectly flat reflections. A flat surface on a continent of jagged mountains and valleys? The best explanation was a liquid surface. In 1969, the first confirmed subglacial lake was discovered beneath Sovetskaya Station in East Antarctica. The door to a hidden world had been cracked open. Since those early days, our toolkit for subglacial cartography has become incredibly sophisticated. Radio echo sounding is still the workhorse. Today, radar systems are mounted on aircraft that fly back and forth in precise grids, methodically mapping huge swaths of the continent. These surveys have given us our first comprehensive maps of the subglacial world, revealing vast mountain ranges and deep canyons. And crucially, the strength of the reflected signal tells us about the ground itself. A strong, flat echo is the classic signature of a subglacial lake. To get an even more detailed picture, scientists also use seismic surveys. Much like geologists searching for oil, they generate sound waves, sometimes using small, contained explosions or specialized vibrating trucks. By listening to the echoes with a series of sensors, They can analyze how the sound travels through ice, water, sediment, and bedrock. This is especially good for mapping the exact depth and shape of subglacial lakes, and even for determining the thickness of the sediment on the lake floor. But perhaps the most revolutionary tool has been the satellite. From space, satellites equipped with incredibly precise laser altimeters, like NASA's ICESAT and ICESAT-2, measure the exact height of the ice sheet's surface. What they found was astonishing. The ice sheet isn't static. In certain areas, it's breathing. The surface rises and falls by several meters over months or years. This movement is a direct result of huge subglacial lakes filling with melt water, which lifts the ice sheet above them, and then draining, causing the surface to subside. By tracking these subtle changes, scientists can map a dynamic, active plumbing system of interconnected lakes and rivers, watching in near real time as vast quantities of water are shuffled around beneath the ice. Using this arsenal of technology, scientists have unveiled a lost world of breathtaking scale and complexity. One of the most stunning discoveries is the Gamburtsev subglacial mountains. Buried under kilometers of ice right in the heart of East Antarctica lies a mountain range the size of the European Alps. Discovered by a Soviet expedition in 1958, their existence was a puzzle for decades. They have sharp, jagged peaks and deep valleys, typical of a much younger, actively forming range. We now know the Gamburtsevs are ancient, but were preserved in their youthful state because they were encased in ice before erosion could wear them down. They are essentially ghost mountains, and scientists believe their high valleys were the very first places where the Great East Antarctic ice sheet began to form. In stark contrast to these buried peaks are the Great Subglacial Basins. The Wilkes Basin, for example, is a massive depression in the bedrock, about 400 kilometers long, and so deep that its floor lies far below sea level. These basins are a major concern for climate scientists. Because their beds slope inwards, away from the coast, they are vulnerable to something called marine ice sheet instability. If warming oceans melt the floating ice shelves that currently act like a cork in a bottle, it could trigger a runaway retreat of the glaciers flowing into these basins, which could have catastrophic consequences for global sea level. But the most dynamic feature of this hidden world is its water. To date, over 400 subglacial lakes have been found. The most famous is Lake Vostok, a colossal body of fresh water, roughly the size of Lake Ontario, buried 4 kilometers beneath Russia's Vostok Station. It has been completely isolated from our atmosphere for at least 15 million years, kept liquid by the Earth's geothermal heat and the insulating blanket of ice above. Its extreme age and isolation make it a unique time capsule, a potential treasure trove of ancient climate records, and a prime target in the search for life. While Lake Vostok appears to be stable and isolated, many other lakes, particularly in West Antarctica, are part of a hyperactive plumbing system. Satellite data shows these lakes, like those in the Whillans ice stream region, regularly fill and drain, transferring huge volumes of water that act as a lubricant at the base of the ice. This watery network directly influences how fast the ice streams flow towards the ocean, making it a critical factor in predicting future sea level rise. The discovery of this vast, dark, cold, energy-limited world immediately raised a tantalizing question. Could anything live there? For decades, the answer was assumed to be no. The first hint that this might be wrong came in 1999. Researchers analyzing ice from the bottom of the Vostok ice core, ice believed to be frozen lake water, found genetic material from microbes. It was tantalizing, but they couldn't rule out contamination from the drilling fluid. To get a definitive answer, they had to go there. They had to drill through kilometers of ice and sample the water directly without contaminating the pristine environment. This was a monumental technological challenge. In January 2013, the WISSARD project successfully drilled into subglacial Lake Whillans, one of the active lakes in West Antarctica. Using a specially designed, sterile hot water drill They retrieved water and sediment samples. The results were groundbreaking. The lake was teeming with life. They found a diverse community of thousands of species of bacteria and archaea. Deprived of sunlight, these microbes have adapted to survive by, essentially, eating rocks. They derive energy from chemical reactions with minerals like ammonium and iron dissolved in the water from the surrounding bedrock. 5 years later, in 2018, the SALSA project drilled into another hidden body of water, Mercer's Subglacial Lake. The findings there were even more shocking. Not only did they find a rich microbial ecosystem, but they also found the preserved carcasses of tiny animals like crustaceans and tardigrades, also known as water bears. This suggests that the area may have been connected to the open ocean more recently than previously thought, perhaps during a warm period thousands of years ago when the ice sheet retreated. These incredible discoveries are the result of massive international collaborations, often coordinated by organizations like the Scientific Committee on Antarctic Research, or SCAR. The scale and cost of working in Antarctica mean that no single nation can do it alone. And the journey is far from over. We have only scratched the surface. What is the full extent of this subglacial plumbing? How does it truly affect the stability of the entire ice sheet? And what other forms of life, with what unique adaptations, are waiting to be discovered in the dozens of other unexplored lakes, especially ancient giants like Vostok? The exploration of Antarctica's subglacial world is not just about understanding our own planet's past and future. It's a dress rehearsal. The study of life in these dark, cold, liquid water environments has profound implications for the search for life on other icy worlds in our solar system, like Jupiter's moon Europa and Saturn's moon Enceladus. As we continue to listen to the echoes from this hidden landscape, we are uncovering a story of immense geological time, remarkable biological resilience, and a future that is inextricably linked to the fate of the ice. The lost world beneath Antarctica is slowly being revealed, and its secrets are changing our understanding of our planet and our place in the cosmos.